let me see. Okay. Today, in the speed something to do with speed. We're going to talk about speed today, and more importantly, how speed add up. Okay. And logical consistency of speed, let's say. And just for bringing this, since this concept is a lot popular, this is what Einstein is well known for. This was mostly first time done by Einstein, right?
Okay.
Tarun, Einstein na pattittu kettittundo? Right, so idu njan parayunna innu parayunna idana Einstein cheyda popular subject on. Okay, so and it doesn't require too much background. So we're going to talk about relativity principle. Relativity, why it is called relativity, I'll describe it in a moment. Simple situation, let's say everything is happening on a line. Road. So this is a road. So we want to interpret this as a road. Okay. Let's say there is an object here. Let's call that G, representing ground. This could be a car, right? This could be a car here. It doesn't have to be moving. And there is another car here. That's this one, let's say, is moving with velocity v. This, let's say, is at rest. Either restilana, either movie, and there is one more car somewhere here in the front. Right, so that is B. And this is also moving, right? But we will bring that in a minute. Okay, so now we have a few more people. Yeah. Hello, Jupesh. Hello, Rishi.
Hi, Shajesh.
Yeah. So I'll intermittently little bit talk in Malayalam also, because we have Tarun and he is in 7th grade. Okay, so
Feel free.
Yeah, so
Feel free to mix in as much Malayalam as is required. Don't worry about us.
Okay, good. Yeah. So again, I was saying that this is a type to talk about relativity principle, and basically, once we define velocity, velocity define cheyidale, speed define cheyidale, logical consistency, and what is the logical consistency required for adding speeds? So let me start by saying everything is happening on a road. It's usually in physics we say it is one-dimensional, but that's not important. Everything is happening on a road. There are 3 cars we will talk about. 3 car, right? This one particularly is going with velocity v. That's an important parameter. This rest. So this is at rest. So this is rest. This is moving, and other moonante car not. One thing we learn very easily is you would take in a distance. Let's call it x, and you would take in a distance. Let's call it x prime. Right? Either 10 meter, either 6 meter. Right? And this distance, let's say, what should I call it? Let's say A, small a. The distances should add up, correct? So that's x is equal to x prime plus a. That should be very clear, right? That's a confusion of entire part. Moon distances add correct? Speed and definition and so speed will be defined as distance over time, but distance in this direction. So it is usually the change in distance. So if this moves a little bit, there is a measurement being made. So that's delta x, let's say, delta x prime and delta a. How much is the change in distance? That's also should be easy. Let us say it's from here to there. Then we are talking about the change in distance from here, change in distance from here, and change in distance from here. Oh, we lost Tarun. Okay. Okay, that was not good. Okay. You guys can see me, right?
Yeah.
Yeah. Okay. Yeah. Give it a half a minute, maybe, just to. Yeah. So Rishi, Bipen, and Jupesh. So basically, I'll talk about what Einstein was popular for. This is special relativity, but I want to develop the relativity principle from logical consistency requirements. We just say that if this is if once we define speed just for logical consistency between different observers, we need to have a requirement, and I'll show that both Galilean relativity and Einstein's relativity is consistent, at least logically consistent, with addition of velocity. So that's broadly what I'll motivate, and then maybe talk about what else could be. Is there something else one can talk about? Okay, so that's going to be the broadly the talk about. Yeah. Any questions there? I think we'll have to give up on Peru. I don't know. Yeah.
No question.
Okay. So let me redo this a little. So since we know when we say this is moving with velocity v, one thing I will say use is that velocity v is equal to change in position over change in time. Whether it is x or y, let's generally say distance, right? Distance over time. That also means that the distance traveled is equal to velocity times time plus a constant. But if I set that constant to be the origin, then distance traveled is equal to velocity times time. So that's the only basic thing we need in this discussion, that distance is velocity times time. We use this intuitively whenever we want to travel somewhere. If the speed limit is something, if the train travels at a certain speed, we can estimate how much time does it take. In that sense, if this is at rest, there is something that I can write immediately, that if this is moving, if this car is moving, this distance, how far A has gone from G, I can immediately say is V times T. This distance is V times T. So just to motivate why one would even consider such simple scenarios, I was going to write this is x. I earlier wrote change in x is equal to change in x prime plus I said a here earlier, and that's delta a. That should be very clear, simple. And if we want to think of velocity in this sense, what you would do is I now want to see how about the velocity measured by g, velocity measured by a of something that is moving, and how is this related to the how do they compare with each other? And one would say that, oh, just divide by time. And one says this is the velocity delta x, right? This is the velocity of b measured with respect to a. Like this also you could have said the same thing. So this is measurement of b with respect to g. This is measurement of b with respect to a. And this is measurement of a with respect to g, if you want. So maybe change the notation a little, sorry. Should have been better. So this is a with respect to g, right? X of a with respect to g, b with respect to a, and b with respect to g. And you would immediately get that velocity of b with respect to a is velocity of b. What did I say? No, with respect to g is plus velocity of a with respect to g. And that's what typically we say, right? I mean, or on an interstate, we all realize that if I'm going with 20 miles per hour and that is going at 30 miles per hour, then relatively speaking, when I say 20 miles per hour with respect to the ground, this is going 30 miles per hour with respect to the ground. If I were to look at this, it seems like it is much slower because you're approaching it, and that's 10 miles per hour. Very standard stuff. But here we have made a big assumption here, notice, is that we are saying that we are going to divide by the same time. And the point is that, is there any other room there? So we have assumed that delta t, the time elapsed between for these two objects, or these two frames, at least the g and a, are exactly the same. And we are going to explore, is there anything else possible? Of course, if time is the same, that's surely one possibility. And I'll show that that's surely one possibility, that there is a consistency in that case. And here we will ask, is there anything else possible? Is it necessary that the time should be the same for these measurements? And then the question is, then t between these two events, right? So TBG and TAG, are they the same? The change in time, are they the same at all or not? So that's the question, and we are going to propose that it is not the same, and we will find a solution that, oh yeah, it is possible that they are not the same. So that's going to be the broad idea that I'm going to explore here. Any questions at this stage?
Right. I think it's fine. Yeah. So I mean, of course, as you have explained that at t equal to 0, the g and a frames origins and their times also coincide.
They should coincide.
So,
yes.
so they have synchronized their clocks at. We say that t equals 0 is when the a is coinciding with g and their origins and clocks are synchronized.
Correct. Very good point. At t equal to 0, so I should add here that at t equal to 0, a and b. So that means to say that at t equal to 0, x ag is equal to x bg, and let's say that's equal to 0. Okay. So that means to say the car is right at g. All three are superimposed at time t equal to 0. It's not that it's beginning from there, it was already moving, but right at that time shot, they're all overlapping at that point. And then since one is slower, one lags behind the other. That's correct. That will be necessary. And I meant to do that. Yeah. In this description, that will be.
No, you didn't mention it. You mentioned it.
Oh, okay. Yeah. So velocity will not depend on that, but since we'll be talking about distances, that will be crucial, especially the time. It will be important. Yes, good point. Yeah. Okay. And again, the point is If the times are the same, we will see that this is all logically consistent. But if time is not the same, also probably there is one possibility. And then I have to talk about what do I mean by logical consistency. So that's going to be the point. So let's say, so let's proceed and okay. So we are going to say that, so this is the same situation here. And this time, let's say, since we are going to talk about time also, so I want to show this as x and t. That is another, so this is G, that's your point A, that's x prime t prime. And this is some object B here, and that's moving, right? That's a car, that's moving. I don't want to give it a specific particular value there, but it's some motion that is going on, and that's what we are trying to describe. This particular A is going with velocity v relative to g. This v is measured with respect to g, and it doesn't matter whether g is moving or not, but it's convenient to choose that to be at rest. Okay. First assumption we will make is that assumption, or I'll motivate why that assumption is necessary, but in this case, it is convenient to look at it as an assumption that the relation between this x prime and a prime and t prime is linear. And why is that relevant? Why should, I mean, when we are really constructing something, why limit yourself to a linear structure at all? And that will be because if it is not linear, whatever equations we write will be dependent on time. Like if it is a t square dependence, the equations or the time dependence will be different tomorrow versus today. The linearity has the simple relation that the change in something is a constant, right? So it remains the same. So today, if I'm traveling, I use one equation, and tomorrow I have to use different equation. That doesn't help too. So usually you call this homogeneity. Right? So we are saying that time is going to be very similar today versus tomorrow, or for that matter, 1 year later. So we'll say both time and space, we will say, is homogeneous in time and space. And that is sufficient for our purposes, that we are all going in straight line. But this can be generalized to more dimensions. That means to say the actual three-dimensional space-time where everything is not going in a straight line. Then you will need isotropy also. So in principle, isotropy means that whether I do my experiment looking towards the north, or whether do I experiment looking towards the east, that should not change. That means to say that my equations should not depend on what direction my lab setup is made, if you want. So in that sense, we don't want any dependence in that. And that is what is meant by isotropy in space. Overall, all this is accommodated by saying that this relation between x with the measurements made in A and measurements made in G are all linear. That means to say that x prime, whatever you measure in this frame versus this, is related by A times x plus B times t. That's it. So two variables, and we want to find out A and B. At this point, I don't know, so it is not very useful. But I'm saying that it is whatever I do, this is all there will be. And let me say this is E and F. Notice the two times measured here are different. And in fact, I have introduced an X dependence in there. Where does this velocity V plane come into picture? The idea is that A, B, E, and F depends only on that velocity V. So that's our statement of the problem, if you want. Can you think of any A, B, E, and F which actually is consistent with what we are going to be measuring. And then I have to say, what do I mean by consistency, right? What should it satisfy? Okay, again, we are finding A, D, E, and F. That's our goal in the mathematical respect. That means to say, if I measure my velocity V here, velocity V there, how are they related, right? That's a question we are asking. And that will require other condition. Now, when I say consistency, what do I mean by consistency? So here is the consistency. I think at least first thing we should have is that there should be a trivial statement in the sense that if this B was A itself, right? Whatever I'm going to propose, that should be satisfied when B is A itself. That means to say that if B is at rest with respect to A, or I can place it right here, then its distance should just stay the same. So that means to say that here, whatever I measure for B with respect to A, so let's say A measures X prime is equal to 0. Remember, this is my X prime and that's my X. So A decides that for all times X prime is 0. That means it is at rest, right? It just doesn't move, like it is right at the place where A is. So it's his hand, let's say. Then what will G measure? G should measure X is equal to, since this is moving and B is moving with A, so that should be VT. So this should be a solution of this. Whatever I propose as my solution here, A, B, E, and F, should satisfy this. Whenever X is equal to VT, I should get X prime equal to 0, or whenever X prime is equal to 0, I should get X equal to VT. That should be an availability in that. So that's what I mean by logical consistency, that at least one of this should be satisfied. Whatever I propose here, that should be satisfied. So go ahead and put this in there, and this we will call it identity, by the way. So this requirement we will call identity. So there will be some 2-3 requirements we will put, and first one is just going to be this. So put this in the first equation. So that's X prime is equal to 0, and A is dependent on V, but sometimes I'll write it, sometimes I will not write it. So whenever I don't write it, there is less clutter in the equation. So sometimes it's more easy to read. So this is X is VT and plus B times T. That should be what it is. And this, if it has to be 0, either T has to be always 0, which is not a very convenient solution. So then we have A times V is equal to B times is equal to B. So I get B is equal to minus V times A. So whatever my B here is, it is related to A. That's what it means. So I had to find 4 unknowns, if you want, and now I have a relation between B and A. If I know A, I know B immediately. So we have made some progress just by requiring that this should satisfy this particular configuration. Remember, this is not always the case. This is just one particular situation we are talking about. For one particular configuration, this is how it should look like. Any questions at this stage?
No, sure.
Okay, thanks. So, okay, so let's proceed then. So if I use that fact, now I have brought my equations to X prime is equal to A times X. Remember, we had A times V, A as a function of V, and then I can write this as x minus vt. Remember, the condition was b is equal to minus v times a, right? So minus v times a immediately gives me my b. And here I have the other equation to be t is equal to e of v times x plus f as a function of v times t. We don't learn much about when we say x prime is equal to 0, x should be equal to vt. We don't learn much on this side. There is no restriction. So we have at least brought it down to 3 unknowns. So the next requirement, third one. So first one was that our universe is homogeneous, or just linearity was an assumption, you can say, but better, it was a requirement from what we expect our space-time to do. And second was identity, a particular configuration. And next, I'll call reverse, right? So let's say this is reversal. It's just a name I'm picking up. So let's say this is the same point here. And let's say this was G, and this is your A, and that's your B. That's something that is happening. This is your movement with velocity V. And remember this, I show this as x prime t prime. That gives me like writing it like that shows that, oh, we have chosen and we have given some preference to going right. Who says that that should be any preference? When I said that space, I mean things should not, or my equations should not depend on whether I'm facing north or east. Here it seems like I have given some preference to going right over left. Right has been chosen. Like typically number system, we choose right as positive and left as negative, but that shouldn't be a requirement at all. So we put that as or let's say I do the same thing now with the reverse now, right? So this is G. Let's say that's A, and that's my B. And everything is happening here. And help me here. Okay, hold on. I think I need better. Okay, so B stays the same. It's only the things that measurement changes, right? So what I'm going to do is that now G is going this way. Yeah, so G is here, and this is your A. So that I'll show as X, and this is T, and this one I'll show as X prime and T prime. And this is moving this time with velocity V. And this really doesn't matter. I could have put it here also. I mean, when you're interested in delta T's, it doesn't really matter. So earlier what I was doing is perfectly fine. The main idea here is that whether I'm like everything is happening here, whether I'm looking at this whole event standing here or behind the board, it doesn't matter, right? Both the observers should measure exactly the same quantity. So then what am I suggesting here? What have I changed here? Basically T prime, T and T prime remain the same. So don't do anything with T. T remains the same, T prime remains the same. But if I were to flip my X, that means X going to minus X. So my requirement is that wherever my X shows, if I were to replace it with minus X, and wherever my X prime is there, if I were to replace it with minus X prime, right, then I'm flipping the system, basically pretending as if everything is going to the left. And if I were to have my velocity also flipped, right? If I do these three requirements, my equations should not change. Yes, Rishi.
Yeah, so you're essentially saying that, in the initial case, we were looking at, the A is moving to the right in G's frame. Now we can look at the whole process in A's frame where G is moving to the left.
Correct.
Right.
No. No, that is going to be coming again. That I will call reciprocity. Whether A is going with respect to G or G is going away with respect to A should be the same. But this I'm not saying that, correct? Here both are moving, like it is the same A that is going away. A going away, A is going away. So what you are trying to say is that in this A is going away, but in the other one G should be going away. But G is at rest, let's say. So this is V is equal to 0 if you want.
No, so with basically, there is a relative velocity between G and A, right?
Correct,
So-
correct. But I'm
so-
not invoking that yet.
So, I mean, whether, so in the frame of G, A has a velocity V to the right,
Mhm.
and in the frame of A, G has a velocity V to the left.
Yeah, I haven't invoked that. See, that's your logic, right? That is your logic saying that.
Huh.
I haven't required that yet. I will require it. Right? See, you're saying that is obvious. That's probably what you're saying. But yes, okay, we'll require that, but I haven't required it in this case. This is not that requirement. This is an independent requirement, I'm saying. Okay. And that is primarily maybe often we don't require this dependence in A. It is not very obvious whether this is even or odd. That's my or that is the reason why I invoke it, because otherwise I will not know whether it's even or not. So I can jump to the next step where you're saying that I'll call that reciprocity. Probably that is sufficient, but at least my argument is that I don't know whether it's an even function or odd function at this point. And you'll see that in a minute when I really do that. So maybe it is a additional feature which may be not necessary, but I feel that's a necessary requirement I'm putting in. So wait for a few more minutes and see if maybe there is a redundancy here. Like you're probably the suggestion or the point you're making is that this is a redundant proposition, maybe. Yeah, but
No,
I think
let's see.
it's needed. Yeah. Okay. So we are saying that this whole thing should be the same, like whether I'm looking at it from this perspective or from the back side, it should be the same. So that's your equation. So I'm going to put this all whenever I do this here, the idea is that they should be the same, like or they should look the same, or they should be consistent. So put this so basically change all the x prime to minus x prime, right? So this is minus x prime is equal to a of minus v, okay, and this is minus x prime, this is equal to plus v of t. T is notice the same, like even though I'm flipping my x, t I don't flip, so there's some condition in there. So this is e of minus v, and sorry, there is no brackets necessary here. That's x plus f of minus v times t, and there is a minus in here, right? So mostly we need to work with the top one. I can multiply by a minus sign immediately and get the fact that this is the same. Right, that's the only main requirement. And then we compare the two, then I can see that that is a requirement here, right? This has to be the same as this, which means to say that whatever my coefficient is a, whether I'm going to the right or to the left, it doesn't matter. And my relative velocity does change my E, but it does not change my F. So let me write that here. So this is A of minus V is equal to A of V, and F of minus V is equal to F of V. These two are identical, but this is an odd function. This is minus of V. So that's what we can learn from this requirement, that this change. We haven't really found anything either A, E, or F, but we just at least know that this has to be even or odd. That is the only thing we have learned. Any questions? Further questions on that? But let me proceed to the next one. Maybe that will fill in the gap clearly. Okay. So remember, first was linear condition. Second was that it should satisfy the identity. Something at rest should look the same. And then this is reversal. Next is what Rishi pointed out, and that's, we will call it reciprocity. So I'll call that reciprocity, but this is a standard name. This is often reciprocity. And now what we are saying is that, so this is one description, that is G, that is A, and there is something happening here. That we said this was moving with velocity V. That was our reference. So remember, this is X prime, that's T prime, and that's your X and T. But now this should be the same whether you discuss it this way, or let's this stay at rest, and this moves backward. So G is now moving backward. Oh, and this is that means to say that whether A is there are two objects moving, and this is why it's called the relativity. The idea of relativity, the word comes in here, is that if two objects are moving, whether I am moving with respect to the other backward, or the other one is moving with respect to me to the front, that cannot be distinguished at all, right? Unless there is another third object with which you can refer to. So between the two, there cannot be any difference. And that's the point, that this is moving to the left or this is moving to the right. This should be the same. That means to say that earlier we had X prime. Let me write that again. And now I want, let me write that, yeah, V dependence in there. And this is X minus Vt, that was our equation. And T prime is equal to E of V times X plus F of V times T. And the requirement we are making is now that if I change my velocity to minus velocity, then my I can keep my X to be the same, X prime to be the same, but V has to change, correct? Is that what I'm saying? Hold on. No, that's not what I'm saying. Okay, help me here. Yeah, I'm wondering whether I want to change my X prime T prime here or not. XT moving. Yeah, I think it is okay. Yeah, so this is sort of the inverse feature of that we are talking. So
We are not changing the signs for x and x prime, right? Only the velocity v.
not the signs, but I think I want to change this, right? I think this I want to change so that I can use this, so that I can use the same equations. Otherwise, I have to think about my inverse. Right? I think this is what I want to do. Yeah, this seems to be reasonable. I think that for I have x and t, and this is moving to the left. So basically, the requirement I'm making is that if I say x, I replace to x prime, and I go t also to t prime. So I change my system itself, and then I change x prime, or basically swap this, right? Put the arrows both sides. So if I swap my x and x prime and v to v prime, v to minus v, then my equations should remain the same. That's fine. Yeah, that's fine.
Yes.
That is described by this, like whether it is going this way or that way. Now I put that in the equations, and that puts in a, that's what I mean by it should be consistent, is that this is x now, that's equal to a of minus v times x prime plus v of t prime. So switch all the, like whatever we said there. So that's t is equal to e of minus v. And this is where I was saying I need that information of whether it is positive, even or odd configuration. So x prime plus f of minus v times t prime. Okay, that's it. Requirement there. Okay. Clear? That's a mathematical requirement. Then there should be some consistency here, right? So put this all together. So now what you basically do is that substitute this x in there, t prime, t in there, and you will get a condition, and it should be consistent. I can do that algebra. It will take only 2 steps, but it's not very insightful. So I'm just going to write down what are the consistency requirements that comes in. So you immediately get a relation that a I'll have to do it. I don't remember it actually. So let me just quickly do this. So x prime is equal to a of v times x, which is a of minus v times x prime plus v times a of minus v. But a of minus v and a of plus v is the same, so we don't have to worry about that. And what am I doing? So t, oh sorry, so that's not what it is. So help me here. What am I doing? X I'm putting this as a minus b x prime plus v. Okay, let me make this better. I'm not going to write the dependence in v in a because that's even, so we don't have to worry about that. So that's x is equal to a times x prime plus v times a times t prime, and next minus v minus v times a, right, and then I'm substituting t,
and then t, which is e of minus
e
minus v
is this
x prime.
X prime, thank you, minus v times a again times f times t prime, correct? I think so. For consistency, the x primes should match. So we have 1 is equal to a square, right? And then there is minus V A square times E of minus V.
How do you get A squared? A into E, right?
Oh, A into.
Oh, there's a A. Okay, there's a A. Oh, okay, fine. Correct. Minus VA squared E. There is A outside here.
Is this correct? Help me. Here.
Yeah.
A
Yeah.
times this times A T prime and minus VA. Oh, I think when I'm putting this minus VA, there is no A here, right? This A is not there.
Yeah.
Right? So there's a mistake in
Yeah. That's how. Let's try.
Yeah. Correct. Okay. Sorry about that. Yeah. Okay. Now it's okay. So then that's better. Okay.
Yeah.
There is no. Okay. I think then I can find E of minus V in terms of this. So this is equal to A square minus 1, right? So it is A square minus 1 over V times A. I'll write that as 1 over V times A minus 1 over A. I think there's no special reason why to write it like that, but that is one way of writing. And we have one more relation here. T prime should also match. T prime is, there are only two terms, A V A square. And this one is correct. Was that okay? So yeah, V, and so sorry, I just have to match this, right? I don't have to put the square. So, or yeah, if we put that, so VA square is minus of VFA has to be equal to 0. But A, if A is 0, that's a solution, but this suggests that A of V is equal to F of V. Or F and the V we have now solved. Notice we haven't used anything except that reciprocity and identity and the reversal in between. So let me summarize what we have as of now, like that mathematical steps where if I don't think that plays significant role in that insight. So put that together. So what we have is three relations. One was linearity, second was identity, and third was I call it reversal, and the fourth was reciprocity. Something we expect in daily life, that we require that we expect this to be true. Based on that, we learned that x prime has to be equal to A times x minus Vt, and T prime, if we want, we said, remember T prime, when the moment we say T prime, we are saying that it's not the same time for every measurement. Every person does not do the same measurement. This is E now, which has a complicated expression from what we noticed there. So this is E times x plus F was A itself, so I'll just write A itself here. So A times T. Okay. Where E came out to be, just for, so whatever we had that, was 1 over V times 1 over A, 1 over A times 1 over. No, E of minus V, right? So this is plus V there. So I have to write this as 1 over A minus A, I suppose. Right. Think so. And now that's all. I mean, based on these requirements, we cannot do further. We still have an unknown here, right? There is an A. Everything we have written in terms of A. And the point is, so now at this point, you come and say that let's just, since we cannot proceed further based on these 4 consistency requirements, next is proposed, right? Let us say that T prime is equal to T. And that's Galilean relativity. So that's Galilean relativity. So this is a requirement now. And then you immediately see that, oh, if that is the case, what are we saying? T prime is equal to T. We set you set A is equal to 1. And if you set A is equal to 1, this is consistent that E is equal to 0. So that's one solution if you want, if you set A is equal to 1, and this is an implied thing, so let me not say E is equal to 0. So that's consistent. So E comes out to be equal to 0. Okay. So that's
E has to be 0, right? If
E has to be 0, but I'm saying that is not a requirement. Right? This came out if you set A equal to 1, 1 minus 1 is 0. Right, so that comes out to be equal to 0. Is that clear what I mean?
If your T prime equation, if your E is not 0, then T prime will not be equal to T because it
That's
will be
true. But remember, E is also equal to this. If I set A equal to 1, then this is 0. So I'm saying to get this T prime equal to T, so this is what I want. I can choose A equal to 1 and I immediately get E equal to 0. So this is, yes, but this is not additional. Do you see what I'm trying to say? Or if you really want me to write, that's perfectly fine, but I'm just saying that this is not an additional requirement.
Yeah. I'm saying that, but it's not possible to have A equals 1 and E not equal to 0 and yet T prime equals T.
Oh, you're saying, is there any other solution in this? To get T prime equal to T. Is
you will be compelled to take E equals 0.
Yeah, I see.
You will be compelled to take E equals 0 as well.
Correct. Yeah, okay.
Because you look at the T prime equation,
yeah,
if A is 1, if your E is not 0, then
that's correct.
So your T prime won't equal T.
That's correct.
For arbitrary X.
Given. Yeah. Okay. So this is so this is a condition. Okay. So for Galilean relativity, an immediate conclusion is that A equal to 1. So and everything is fine with that. And so Galilean relativity is a possible relativity principle. So what the conclusion will be that whatever we wrote, if we use Galilean relativity, it is a consistent relativity principle. Nothing wrong in that. And then we ask, is there anything else? Like, is there anything else also that can satisfy these 4 relation? And that is where Einstein's thing came up, but he did not look at it this way. But even though he had all these things discussed in it, so mute. Okay, so the other possibility is that, so what was the why did Einstein had to come up with? Einstein realized or he tried to understand Maxwell's work, and in Maxwell's work it turns out that there is the speed of light in vacuum, c. So when v is equal to c, this is independent of frame. Whoever is measuring this comes out to be the same. What that means is that whether our observer, so there is this again our straight line that is this x and p, that is this x prime and p prime, and it is moving with velocity v. But if that was measuring the speed of light, that is c, they will measure the same. That means to say, if x, this frame measures this as x equal to ct, because this is moved to the right. As far as this frame goes, this is x is equal to ct. But A would say, this was G, A would say that it is x prime is equal to ct prime, like in its prime there is a t prime there. And these two equations is what comes out, but they will measure the same speed, notice. That is very different from what Galileo would have said. They would have said that there is a relative difference between them. There is a speed. It doesn't mean that there is everything can happen, or we could ask, are there two speeds that can do this job? But to begin with, we are saying that there exists at least one effect, even if it is not speed of light, there at least is one effect which is identical to these two frames, one effect related to velocity, let's say. So that is a speed which remains the same, and that requirement shows up in that form. If that is the case, we go back and put this in, right? We have our equations, and if I put these two in, I should get some condition there. So x prime is equal to c times t prime, and that's equal to a times x is equal to ct minus vt, and t prime so this is true, and I'm just replacing all my x's, right? That's all I'm doing. X prime is, or let me write this as it is, and t prime, and this is e, x is ct plus a times t. This should be consistent, so I can divide this out, right? If I divide these two equations, time t prime goes away from the left and t goes away from the right, so I get a relation that c, let me do the opposite. So it is 1 over c, so I'm dividing the second equation, and first equation is in the denominator. So that's equal to e times c plus a divided by a times c minus v. That's a consistent relation, and we can immediately see that that implies that gives a solution for a. I can do that in a minute here. Would have liked it to be a much more cleaner discussion, but I think too much algebra going in. So this is c minus v over c. I brought it to the left. So this is e e times c over a plus 1. E, remember, was 1 over v times 1 over a minus a plus 1, and this is c minus, so that's 1 minus v over c. So this comes out to be equal to 1 cancels out. I have c over v, that's 1 over a square, and a cancels out, and that is minus c over v. Right? Did I do all this correct? Yeah, I think so. 1 cancels out, bring this c over v on the other side, so I have v square over c square is equal to 1 over a square, and bring that 1 on this side. So that's 1 here. And so we have A is equal to 1 over 1 minus V square over C square. So overall, what we are saying is that instead of setting A equal to 1, if I were to set A is equal to 1 over 1 minus V square over C square, right, where remember my X prime is equal to A times X minus VT, and T prime then is equal to, I can put this all together, it becomes A. I can bring that A out and it comes out to be equal to minus Vx plus T, I suppose. Oh, that is C squared times T. That comes out to be a solution. So again, here there is this time is no more like the Galilean times are different for different observers, and that's Einstein's relativity. But this should sort of raise a question as to just to motivate, is there any other solution in here, right? Can we require or can we expect that there is something else also that might be consistent with what we call relativity principle? By relativity principle, we mean that those 4 relations there and 4 conditions that we put, that is satisfied by a linear set of equations. So that's sort of the 2 solutions I was trying to motivate. I don't know if it was very insightful or not. I felt I got involved with the algebra in there. Yeah. Any questions? Thoughts, comments?
So no, so actually, I mean, this is very neat. In fact, sorry, yeah, this was quite neat actually. As you put it, based on just the logical consistency of the expectations. How far can we go? And actually, we can actually derive the so-called Lorentz transformation equation, which relates to 2 different frames. Just in case, I don't know, I mean, Dipan Kumar and Dipesh are aware that these equations tell you that simultaneity is no longer a frame independent. This T prime and T, the relation tells that what is constituted as simultaneous in, say, A or G, what is simultaneous in A frame need not be simultaneous in G frame.
Correct.
So simultaneous, I mean, the radical consequence of these equations is that the lengths and time scales are no longer absolute. They have to be referred to a given frame.
Correct. And another thing I'd like to point out here at this point is that there is the speed of light being the effect that we say is the same. But is it possible that there are 2 speeds that are the same at all? For example, I think this is discussed in the following way. We have electromagnetic waves which travel at the speed of light in vacuum. Gravity is entirely different, and they also have a wave associated with them. And the expectation is that why should the speeds be the same? Like their speeds. Is it possible at all that there is a different speed for gravitational waves and a different speed for electromagnetic waves? But it seems like this logical inconsistency has nothing to do with Maxwell's equation at all. This is more like a physical requirement, like logical requirement in a way, that there is a maximum speed.
Yeah.
Since we discovered Maxwell's equations first, we said that is speed of light, and it turns out that there is only 1 speed possible, because the moment you say it's a maximum, there's only 1 possible there, right? And that makes the other speed also to be the same, which can be kind of puzzling in a sense that 2 independent fields have the same speed. But seen this way, it is okay. Seems like that's only possible. So,
Oh.
yeah, that's it.
Yeah. So I'd just like to make one comment. I mean, as you put it towards the end, that I think the key takeaway from all this general discussion is that I think the way relativity has been discussed, it is often about the speed of light, but the essence of relativity is actually not the speed of light. It puts a limit on the maximal speed of a signal propagation. Okay.
Correct.
Now, when you say that there is a limit to a maximal speed of signal propagation, it has to be frame independent. Because you cannot have a maximal speed and it cannot depend and cannot have it depend on a frame. Because if it depends on a frame, then you can go to another frame and jack it up. Right?
Correct. Yeah.
So maximal meaning it has to be frame independent. Otherwise, maximal has no frame dependent meaning. So the essence of the relativity principle is not that the speed of light is that speed of light is the ultimate speed, that there exists a limit to the signal propagation. That means there is a maximal speed, and once it is acknowledged as maximal, it has to be logically, it has to be frame independent.
Correct. Yeah. It has nothing to do with Maxwell's equation or optics or anything. That's
now this they have this question about how come the two different waves like gravitational waves and electromagnetic waves happen to have the same maximal propagation. Okay. So I don't know. I mean, just from the top of the head, if you look at this, the maximal speed is going in this equation, right? So now, if you put V equals C.
In this.
Okay. Yeah. So if you put V equals C, your denominator, blows, right?
Yeah.
Your A blows.
This goes to infinity.
Yes. Now, if okay, so the question that one needs to pose is that when you go from here to say, because now this will have implications. Okay, we have not discussed it today, but this will have implications about the total energy and the momentum and how we define the velocity, right?
Yes. Yeah.
So these has implications. And now, momentum. See, any classical particle, how do we define something as a particle? Our classical notion is that it has a mass and that it can sustain a force whose effect is given by m times a, and that it can be a carrier of momentum, which is given as m times v, right? Now, the point is that how do you define the momentum? Because if it is m times v, if we carry this logically forward, this relativity principle, then it turns out that there is something called rest mass. Okay, and a relativistic mass.
Yeah,
which is different from the rest mass.
yes.
So then the question is momentum rest mass times velocity or relativistic mass times the velocity? Right. So when one bothers about these questions, it turns out that you can either define the momentum as relativistic mass times the ordinary velocity, in which case the relativistic mass is mass divided by this factor, square root of 1 minus v squared by c squared.
Yeah.
So you can just write m. You can just write p equals
M effective, let's say, is m naught.
m naught by 1 minus v squared by c squared. Now, if you write momentum as m effective times v,
Or
even now you can forget about even writing the momentum. You can ask this question as to what would be the effective mass of a particle traveling at the velocity of light? V equals C if you put it,
Correct.
right?
Mhm.
So it becomes indeterminate. I mean, only if M naught is 0, it
Mhm.
makes sense. So such a particle
Yes.
cannot sustain an ordinary momentum
Mhm.
in the ordinary sense. It cannot sustain a force. It cannot have a kinetic energy in the ordinary sense. So then how do we define the energy for such a particle? If it does not, how do we define the momentum for such a particle?
How do we define? Yeah.
And how do we define the energy for such a particle?
So only possibility is that M naught has to be equal to.
Yes, so M naught, that means such a particle has to have a rest mass equal to 0.
Correct.
Right. Now if the M naught is 0, then how do we define the energy for such a particle? Okay. Because if you look at the expression for the energy, it is E squared is P squared C squared plus M squared C4, right?
Yes, and that is
So
I have not
if you just
written that here. So
just
I think,
write down.
yeah, so it will be energy will be equal to just, I think it is 1 over V square over C square and just M, I suppose. Yeah, this is it. And MC square.
Yes.
Yeah.
Right, that is M naught. Is the M naught.
And not in this way.
Yeah.
Yes.
Now, of course, now this expression will not help us if one wonders about the energy of a relativistic particle which is moving with velocity of light. Then this expression does not help for the energy because V is C, and so
If
M
this
naught
is
has to be
P,
0.
then this is equal to, so yeah, this doesn't
This
help.
is indeterminate
So
because M
M
naught has
naught
to be
is
0.
equal to 0 and V tending to C, that maybe there is some constant, right? That could be a finite amount.
So that's why you can write Shajesh.
Uh-huh.
The energy in the other form, E squared is P squared, C squared plus M squared C4.
Yes.
Which is
Let me write it here. That is still visible, right? Yeah.
Yeah.
So this is E square is equal to P square. And you want M naught, I suppose, right?
Now see, so this expression comes to our rescue. Both these expressions are equivalent, but the one with MC squared by square root of 1 minus C squared does not help us when the M naught is 0. But now this gives you E equals PC for a particle with relativistic, I mean, with moves with velocity of light. So that means the momentum of a particle is E by C. You cannot, I mean, you can see that you cannot define the momentum from M naught V wala jo expression hai, that will not give you the momentum for the particle whose mass is 0, right?
Yes. So
but this expression gives you E by C. This expression will not help when the M naught is 0. And M naught is 0 is the only possibility when V is C.
Correct.
Right. So that's why you can, so when V is C, this expression cannot give you momentum.
Yes. Yeah.
Right. So that's why one has to go to the upper expression where P becomes E by C. Okay. So you can write P by E, E is equal E by C.
P is equal to E.
So for a particle which moves with velocity of light, the momentum is given by E by C, right? So now the question is, different momentum, meaning it boils down to now this is just a, that means momentum is essentially energy times the constant, right? So the question is, how does one differentiate particle of different momenta? So they are different, they are differentiated by different energy. But then how does one differentiate particles with different energy, right? So it turns out that such a particle, one differentiates different energy by different frequencies. So it is compelled to, what I'm trying to say is that there is no way to understand a particle moving with velocity of light in classical physics. Such a particle, the energy is given as h nu.
Yes.
So M equals 0 particles are the legitimate progeny of relativity and quantum mechanics. There is no way to understand, make sense of them within pure relativity or pure classical mechanics.
Reasonable. Yeah.
And that's why, when we talk about, so now this helps us understand that, why gravitational waves should have the similar this thing. Because if gravitational waves are believed to be, carried by the massless particles called graviton, just as electromagnetic force is carried by photons, which are massless. Okay,
Mhm.
there is no other way for them to travel but to travel with velocity of light.
Yes, yes, agreed.
So I mean, so this way one can make sense that gravitational waves and electromagnetic waves both have to travel with maximal speed. That
Yes,
is,
yeah,
and then that's why both have to be a legitimate progeny of relativity and quantum mechanics, because there is no way to make sense here. E will be proportional to frequency.
yeah. Or you're saying gravity has to be quantum at that.
Exactly.
Yeah. Like if they have the same speed, which way they have.
Yes, which we
Yeah.
That's why we must worry about quantizing gravity. It's not just a question of should we quantize it or not. Logical consistency requires that you have to quantize it.
Yeah. Good. This was useful. Yeah. Okay. Yeah. So this was good. I think we still crossed time. I was trying to.
Yes.
Time. Yeah.
But this was very interesting, Shajesh. I really liked it. It's quite neat because here, the beautiful thing is that one does not really have to, bring in the Maxwell's equations or the Michelson's experiment. And of course, I mean, this ultimately the experimental base has to be borne out by Michelson's experiment.
Of course. Yeah. But this is just basic logic enforces this or
Yes.
puts it on
Very
our
neat.
lap. Yeah.
I have a question, Shajesh.
Yes, please. Yeah.
I was wondering if this homogeneity and isotropy. Okay, we are imposing the homogeneity and isotropy, right?
Yes.
I mean, it's a crucial element in going into this.
Correct.
Now, can I say, if I look at the two relativity principles, the two postulates that the velocity of light is a frame-independent constant, and that the laws of physics are same in all Lorentz frames, right? Now, if I once I subscribe to these postulates that the laws of physics are same in all inertial reference frames, then does it imply the homogeneity and isotropy of space? Should it? I would naively tend to think that it should imply the homogeneity and isotropy, because if the space is not homogeneous and isotropic, then
I think so, because by homogeneity and isotropy, we mean this, that it is X independent, correct?
Exactly.
If I make any small changes, it is the same. And
yes.
Lorentz has this, Lorentz transformation has this linearity in it. I would expect that to be the case, but then there might be some subtle things, and there's always this.
Okay, so I tend to think that it's, as far as we are talking about special relativity, when you say that the laws of physics are frame independent, then obviously that would mean that I could choose one frame to be moving at a velocity at some other angle, right? With the original frame, it can make an angle, and if the laws of physics are same, isotropy has to be implied, right?
Correct.
And that I can choose whatever velocity. So I think even homogeneity, because I did not choose the origins to coincide. Because if homogeneity is not implied, then laws of physics will not be same at all the points, right?
Correct. And like we might be able to look into the metric and see, right? But usually we work with the metric. We don't really write down the general transformations, right? Like in general relativity, you go beyond this, and there the requirement is, for example,
that is more complex.
Yeah. But I think if what you're saying is that does this imply that or not? And
because metric is a consequence of the assumptions, right? Metric is a consequence of.
Yes, it's a consequence. But there I'm saying we do assume homogeneity in space, right? Like Schwarzschild is no, Schwarzschild is not homogeneous, but we say that it is isotropic. It
Yeah,
is
exactly.
homogeneous in time. Schwarzschild is homogeneous in time and isotropic in space, but not homogeneous. Yeah.
Yeah.
So we should see that it is, as far as time goes, it should have the Lorentz structure in it. It should be linear in time.
Yeah.
But
No,
as
actually,
far
so
as
I am not right now. I would say that, because I looked at the discussion on this homogeneity and isotropy in the Misner-Wheeler-Thorne. And if one really wants to carry out this discussion of homogeneity and isotropy for arbitrary manifolds, okay, then it's quite subtle and it's not really. I mean, it's not, the discussion is not very obvious to me. Let's say I'm restricting myself to the flat Minkowskian space-time, where things are flat and the metric is whatever the signature that it has for the Minkowski space-time. But if you talk of a very complex manifold, arbitrary curved and all that, then this requirement perhaps has very non-trivial assumptions about the manifold.
I agree. Yeah, one should be careful because it's not necessarily the straightforward solutions we are talking about. That could be a non-trivial solution, and even that is valid. Yeah. So one would think so that the inverse is true, but maybe not. Yeah, it's not obvious.
Yeah. So in cosmology, one begins with this, this Robertson-Walker metric, which assumes that universe. See this, even the homogeneity and isotropy of the universe. Okay, I think this is just for the people who may not be exactly from physics. So the statement that homogeneous and isotropic, as Shajesh told, is that universe is same. Okay. So there are two aspects to this discussion. One is that again, I think we need to distinguish two different things. One is that the space, empty space-time is same at every point. That means under identical conditions, if you perform experiment here and in Andromeda or anywhere else in other corner of universe, under identical conditions, you will yield same results. Experimental results will not be able to pinpoint whether it was conducted on this corner of universe or that corner of universe. Okay, so this is the homogeneity and isotropy, that that all directions are a priori same, all time instances are same. That means Jyotish has no place in science, that all moments are equivalent. There are no more sacred time moments or more important time moments. Everything has been equal. There are all, but what Shajesh is talking about the metric, there I think, Shajesh, we have to now worry about the mass distribution, right? Which need not be, I have a distribution of mass which need not be, and when you say the universe is, the distribution of mass in universe is homogeneous and isotropic, it is only at the certain length scales, right? It is at the clusters of galaxies that it is homogeneous. If you look at the solar system level or galactic level, it's not homogeneous, right?
True. Yeah.
So this homogeneity is at the level of some mega parsec level, So that means if one takes a snapshot of the entire universe at the clusters, each cluster has a dot, clusters of galaxies, clusters of thousands of galaxies as one dot, then it is the homogeneity at that scale.
Yes.
So
yes,
and distribution is
and one
thing.
can ask what will be the error associated with this, right? Yeah, when we make that approximation that this is not really homogeneous. What is the
not at the local scale?
Yeah.
Local scale, you can see there is a so much distance between Earth and Sun, right?
Of course.
So, but
good point.
But
no, this was this is a good point. Yeah. And even the boundary itself, right? And it has a lot of questions there. Yeah.
Yes. Boundaries make things, then the whole discussion of topology and these things enters, I mean.
Yeah.
One has to classify the manifolds differently and then talk about the properties.
True. No, good point. Yeah.
But nice, Shajesh, I enjoyed. I mean, I never looked at Lorentz transformation from this point of view.
I thought, I felt it is logical
Yes, yes.
instead
I think this is in principle accessible to, just that, I think people are generally not used to some algebra. I mean, in the standard this thing. So when it becomes algebraic, people who are not used to on a daily bread and butter basis.
yeah, yeah.
But,
Yeah, I would have liked to reduce that algebra, but I was not.
no, but you can't actually. Beyond a point in relativity, see the geometry is hyperbolic, right? So it will be a quadratic and, the hyperbolic geometry. So there will be those negative signs and all that. So beyond a point, it cannot be.
Agreed. Yeah. But good. Yeah. So,
I just want to, just connection to
yeah, please. Yeah.
Einstein made this very beautiful remark. I think it's a very profound remark. Make it as simple as possible, but not simpler.
Not simpler, yes.
So I think that's a very profound remark. And I think it is as simple as it could get. Making it more simple than this would be simpler and would not do justice to the idea of relativity.
Yeah. Good point.
That's a very profound remark.
So that was really said by Einstein?
Yes.
Okay.
Yes.
Okay.
This quotation is attributed to Einstein.
Interesting. Yeah.
Now, come to think of it, it's actually very profound.
Of course. Because it's very easy to go to that.
Yes.
Yeah, especially when you go to pedagogy, like it's always a choice that, maybe I can give up on precision and.
Yes, and then you are not talking of relativity, you are talking of something else.
Yeah. Good. Nice. Okay, so
Thanks.
at least let me stop the recording, then we can stay as